Question 8. A hollow cylindrical tube, sealed at the bottom and open at the top, floats vertically in a liquid as shown. The tube contains only air, and no liquid enters the tube. The height of the tube is 0.60 meters. When floating at rest, the liquid level outside the tube is 0.40 meters above the bottom of the tube. The cross-sectional area of the tube is 0.012 square meters, and the weight of the tube is 30 newtons. Atmospheric pressure acts on all exposed liquid surfaces. What is the density of the liquid? This question tests our understanding of buoyancy, Archimedes' principle, and the principle of flotation. So, what do we know? Archimedes' principle states that a floating or submerged object experiences an upward buoyant force equal to the weight of the fluid displaced. We also know that this buoyant force, sometimes called the upthrust, can be calculated using the formula buoyant force equals density of the liquid multiplied by g multiplied by the volume of liquid displaced. Finally, for a floating object in equilibrium, the downward weight of the object is balanced by the upward buoyant force. Now let's dive into the main solution. We begin by recalling the expression for the buoyant force acting on an object in a fluid. The buoyant force equals the density of the liquid multiplied by g multiplied by the volume of liquid displaced. Next, we determine the volume of liquid displaced by the tube. Because the tube has a uniform cross-sectional area, as it is cylindrical, the displaced volume can be calculated as the cross-sectional area multiplied by the submerged height. So, the displaced volume equals A multiplied by the submerged height. Substituting this into the buoyant force expression gives buoyant force equals density of the liquid multiplied by G multiplied by A multiplied by the submerged height. Now consider the equilibrium condition. Since the tube is floating at rest, the upward buoyant force must equal the downward weight of the tube. So, the weight of the tube equals the buoyant force. Therefore, weight of the tube equals density of the liquid multiplied by G multiplied by A multiplied by the submerged height. Next, we rearrange this equation to make the density of the liquid the subject. Density equals the weight of the tube divided by G multiplied by A multiplied by the submerged height. Now we substitute the values given in the question. The weight of the tube is 30 newtons. G is approximately 9.81 meters per second squared. The cross-sectional area, A, is 0.012 square meters. The submerged height is 0.40 meters. Substituting these values gives density equals 30 divided by 9.81 multiplied by 0.012 multiplied by 0.40. Evaluating this expression gives approximately 6.4 times 10 to the power of 2 kilograms per cubic meter. So, the density of the liquid is approximately 6.4 times 10 to the power of 2 kilograms per cubic meter. This is our final answer for the density of the liquid. So what did we do? First, we used Archimedes' principle, which states that the upthrust equals the weight of the liquid displaced. Then, we calculated the displaced volume, using the cross-sectional area of the tube and the submerged height. After substituting this volume into the buoyant force equation, we equated the buoyant force to the weight of the tube, because the tube is floating in equilibrium. Finally, we rearranged the equation and substituted the given values to calculate the density of the liquid. A common mistake in problems like this is to use the full height of the tube when calculating the displaced volume. However, only the submerged part of the tube contributes to the displaced volume. And so, always identify the submerged height before applying Archimedes' principle. In this case, using the full height of the tube as the displaced depth incorrectly assumes that the tube must be completely submerged. We are done with the solution. Let's recap on the key points. A floating object is in equilibrium when the upthrust acting on it equals its weight. The buoyant force depends on the volume of liquid displaced, not the total size of the object. For objects with uniform cross-section, the displaced volume is found by multiplying the cross-sectional area by the submerged height.